3D printing, also known as additive manufacturing, refers to various processes used to synthesize a three-dimensional object. In 3D printing, successive layers of material are formed under computer control to create an object. These objects can be of almost any shape or geometry, and are produced from a 3D model or other electronic data source. A 3D printer is a type of industrial robot. Futurologists such as Jeremy Rifkin believe that 3D printing signals the beginning of a third industrial revolution, succeeding the production line assembly that dominated manufacturing starting in the late 19th century. Using the power of the Internet, it may eventually be possible to send a blueprint of any product to any place in the world to be replicated by a 3D printer with element links, capable of being combined into any material substance of any desired form. 3D printing in the term's original sense refers to processes that sequentially deposit material onto a powder bed with inkjet printer heads. More recently, the meaning of the term has expanded to encompass a wider variety of techniques such as extrusion and sintering-based processes. Technical standards generally use the term additive manufacturing for this broader sense. History, terminology and methods. Early additive manufacturing equipment and materials were developed in the 1980s. In 1981, Hideo Kodama of Nagoya Municipal Industrial Research Institute invented 2M fabricating methods of a three-dimensional plastic model with photo-hardening polymer, where the UV exposure area is controlled by a mask pattern or the scanning fiber transmitter. Then in 1984, Chuck Hull of 3D Systems Corporation developed a prototype system based on a process known as stereolithography, in which layers are added by curing photopolymers with ultraviolet light lasers. Hull defined the process as a system for generating three-dimensional objects by creating a cross-sectional pattern of the object to be formed, but this had been already invented by Kodama. Hull's contribution is the design of the STL file format widely accepted by 3D printing software, as well as the digital slicing and infill strategies common to many processes today. The term 3D printing originally referred to a process employing standard and custom inkjet print heads. The technology used by most 3D printers to date, especially hobbyist and consumer-oriented models, is fused deposition modeling, a special application of plastic extrusion, and processes for metal sintering or melting usually went by their own individual names in the 1980s and 1990s. At the time, nearly all metalworking was produced by casting, fabrication, stamping, and machining, although plenty of automation was applied to those technologies. The idea of a tool or head moving through a 3D work envelope, transforming a mass of raw material into a desired shape layer by layer, was associated, by most people, only with processes that removed metal, such as CNC milling, CNC EDM, and many others. But M-type sintering was beginning to challenge that assumption. By the mid-1990s, new techniques for material deposition were developed at Stanford and Carnegie Mellon University, including microcasting and sprayed materials. Sacrificial and support materials had also become more common, enabling new object geometries. The umbrella term additive manufacturing gained wider currency in the decade of the 2000s. As the various additive processes matured, it became clear that soon metal removal would no longer be the only metalworking process done under that type of control. It was during this decade that the term subtractive manufacturing appeared as a retronym for the large family of machining processes with metal removal as their common theme. However, at the time, the term 3D printing still referred only to the polymer technologies in most minds, and the term AM was likelier to be used in metalworking contexts than among polymer, inkjet, stereolithography enthusiasts. The term subtractive has not replaced the term machining, instead complementing it when a term that covers any removal method is needed. By the early 2010s, The terms 3D printing and additive manufacturing developed senses in which they were synonymous umbrella terms for all AM technologies. Although this was a departure from their earlier technically narrower senses, it reflects the simple fact that the technologies all share the common theme of sequential layer material addition, joining throughout her 3D work. Envelope under automated control have been desktop manufacturing, rapid manufacturing, as the logical production level successor to rapid prototyping, and on-demand manufacturing, which echoes on-demand printing in the 2D sense of printing. The 2010s were the first decade in which metal parts such as engine brackets and large nuts would be grown in job production rather than obligately being machined from bar stock or plate. As technology matured, several authors had begun to speculate that 3D printing could aid in sustainable development in the developing world. General principles. Modeling 3D printable models may be created with a computer-aided design package, via a 3D scanner or by a plain digital camera and photogrammetry software. 3D printed models created with CAD results in reduced errors and can be corrected before printing, allowing verification in the design of the object before it is printed. The manual modeling process of preparing geometric data for 3D computer graphics is similar to plastic arts such as sculpting. 3D scanning is a process of collecting digital data on the shape and appearance of a real object, creating a digital model based on it. Printing. Before printing a 3D model from an STL file, it must first be examined for errors. In fact, most of the CAD softwares produced errors in the STL files. Holes, faces, normals, self-intersections, noise shells or manifold errors. This step being called repair, as the original model is needed to be fixed. Generally, STLs that have been produced from a model obtained through 3D scanning often have more of these errors. This is due to how 3D scanning works, as it's often point-to-point acquisition. Reconstruction will include errors in most cases. Once completed, the STL file needs to be processed by a piece of software called a slicer, which converts the model into a series of thin layers and produces a G-code file containing instructions tailored to a specific type of 3D printer. This G-code file can then be printed with 3D printing client software. Printer resolution describes layer thickness and XY resolution in dots per inch or micrometers. Typical layer thickness is around 100 micrometers, although some machines can print layers as thin as 16 micrometers. XY resolution is comparable to that of laser printers. The particles are around 50 to 100 micrometers in diameter. Construction of a model with contemporary methods can take anywhere from several hours to several days, depending on the method used and the size and complexity of the model. Additive systems can typically reduce this time to a few hours, although it varies widely depending on the type of machine used and the size and number of models being produced simultaneously. Traditional techniques like injection molding can be less expensive for manufacturing polymer products in high quantities, but additive manufacturing can be faster, more flexible and less expensive when producing relatively small quantities of parts. 3D printers give designers and concept development teams the ability to produce parts and concept models using a desktop-size printer, finishing though the printer-produced resolution is sufficient for many applications. Printing a slightly oversized version of the desired object in standard resolution and then removing material with a higher resolution subtractive process can achieve greater precision. Some printable polymers such as ABS allow the surface finish to be smoothed and improved using chemical vapor processes. Some additive manufacturing techniques are capable of using multiple materials in the course of constructing parts. These techniques are able to print in multiple colors and color combinations simultaneously, and would not necessarily require painting. Some printing techniques require internal supports to be built for overhanging features during construction. These supports must be mechanically removed or dissolved upon completion of the print. All of the commercialized metal 3D printers involve cutting the metal component off of the metal substrate after deposition. A new process for the GMAW 3D printing allows for substrate surface modifications to remove aluminum or steel. Processes. Several 3D printing processes have been invented since the late 1970s. The printers were originally large, expensive, and highly limited in what they could produce. A large number of additive processes are now available. The main differences between processes are in the way layers are deposited to create parts and in the materials that are used. Some methods melt or soften the material to produce the layers, for example, selective laser melting or direct metal laser sintering, selective laser sintering, fused deposition modeling, or fused filament fabrication, while others cure liquid materials using different sophisticated technologies, such as stereolithography. With laminated object manufacturing, thin layers are cut to shape and joined together. Each method has its own advantages and drawbacks, which is why some companies offer a choice of powder and polymer for the material used to build the object. Others sometimes use standard, off-the-shelf business paper as the build material to produce a durable prototype. The main considerations in choosing a machine are generally speed, costs of the 3D printer, of the printed prototype, choice and cost of the materials, and color capabilities. Printers that work directly with metals are generally expensive. However, less expensive printers can be used to make a mold, which is then used to make metal parts. Extrusion deposition. Fused deposition modeling derives from automatic polymeric foil hot air welding system, hot melt gluing, and automatic gasket deposition. Such principle has been further developed by S. Scott Crump in the late 1980s and was commercialized in 1990 by Stratasys. After the patent on this technology expired, a large open-source development community developed in both commercial and DIY variants utilizing this type of 3D printer appeared. As a result, the price of this technology has dropped by 2 orders of magnitude since its creation. In fused deposition modeling, the model or part is produced by extruding small beads of material which harden immediately to form layers. A thermoplastic filament or metal wire that is wound on a coil is unreeled to supply material to an extrusion nozzle head. The nozzle head heats the material and turns the flow on and off. Typically, stepper motors or servo motors are employed to move the extrusion head and adjust the flow. The printer usually has 3 axes of motion. A computer-aided manufacturing software package is used to generate the G-code that is sent to a microcontroller which controls the motors. Extrusion in 3D printing using material extrusion involves a cold end and a hot end. Various polymers are used, including acrylonitrile, butadiene, styrene, polycarbonate, polylactic acid, high-density polyethylene, PC, ABS, polyphenyl sulfone, and high-impact polystyrene. In general, the polymer is in the form of a filament fabricated from virgin resins. There are multiple projects in the open-source community aimed at processing post-consumer plastic waste into filament. These involve machines used to shred and extrude the plastic material into filament. Additionally, fluoropolymers such as PTFE tubing are used in the process due to the material's ability to withstand high temperatures. This ability is especially useful in transferring filaments. FDM is somewhat restricted in the variation of shapes that may be fabricated. For example, FDM usually cannot produce stalactite-like structures, since they would be unsupported during the build. Otherwise, a thin support must be designed into the structure, which can be broken away during finishing. Fused deposition modeling is also referred to as fused filament fabrication by companies who do not hold the original patents like Stratasys does. Binding of granular materials. Another 3D printing approach is the selective fusing of materials in a granular bed. The technique fuses parts of the layer and then moves upward in the working area, adding another layer of granules and repeating the process until the piece has built up. This process uses the unfused media to support overhangs and thin walls in the part being produced, which reduces the need for temporary auxiliary supports for the piece. A laser is typically used to sinter the media into a solid. Examples include selective laser sintering, with both metals and polymers, and direct metal laser sintering. Selective laser sintering was developed and patented by Dr. Carl Deckard and Dr. Joseph Beeman at the University of Texas at Austin in the mid-1980s, under sponsorship of DARPA. A similar process was patented without being commercialized by R.F. Householder in 1979. Selective laser melting does not use sintering for the fusion of powder granules but will completely melt the powder using a high-energy laser to create fully dense materials in a layer-wise method that has mechanical properties similar to those of conventional manufactured metals. Electron beam melting is a similar type of additive manufacturing technology for metal parts. EBM manufactures parts by melting metal powder layer by layer with an electron beam in a high vacuum. Unlike metal sintering techniques that operate below melting point, EBM parts are void-free. Another method consists of an inkjet 3D printing system. The printer creates the model one layer at a time by spreading a layer of powder and printing a binder in the cross-section of the part using an inkjet-like process. This is repeated until every layer has been printed. This technology allows the printing of full-color prototypes, overhangs, and elastomer parts. The strength of bonded powder prints can be enhanced with wax or thermoset polymer impregnation. Lamination. In some printers, paper can be used as the build material, resulting in a lower cost to print. During the 1990s, some companies marketed printers that cut cross-sections out of special adhesive-coated paper using a carbon dioxide laser and then laminated them together. In 2005, MCOR Technologies Limited developed a different process using ordinary sheets of office paper, a tungsten carbide blade to cut the shape, and selective deposition of adhesive and pressure to bond the prototype. There are also a number of companies selling printers that print laminated objects using thin plastic and metal sheets. Photopolymerization stereolithography was patented in 1986 by Chuck Hull. Photopolymerization is primarily used in stereolithography to produce a solid part from a liquid. This process was a dramatic departure from the photosculpture method of François Willem developed in 1860 and the photopolymerization of Mitsubishi's Matsubara in 1974. The photosculpture method consisted of photographing a subject from a variety of equidistant angles and projecting each photograph onto a screen, where a pantograph was used to trace the outline onto modeling clay. In photopolymerization, a vat of liquid polymer is exposed to controlled lighting under safe light conditions. The exposed liquid polymer hardens. Polymerization occurs when photopolymers are exposed to light when photopolymers contain chromophores. Otherwise, the addition of molecules that are photosensitive are utilized to react with the solution to begin polymerization. Polymerization of monomers lead to cross-linking, which creates a polymer. Through these covalent bonds, the property of the solution is changed. The build plate then moves down in small increments and the liquid polymer is again exposed to light. The process repeats until the model has been built. The liquid polymer is then drained from the vat, leaving the solid model. The EnvisionTech Factory is an example of a DLP rapid prototyping system. Inkjet printer systems like the Objet PolyJet system spray photopolymer materials onto a build tray in ultra-thin layers until the part is completed. Each photopolymer layer is cured with UV light after it is jetted, producing fully cured models that can be handled and used immediately, without post-curing. The gel-like support material, which is designed to support complicated geometries, is removed by hand and water jetting. It is also suitable for elastomers. Ultra-small features can be made with the 3D micro fabrication technique used in multiphoton photopolymerization. This approach uses a focus laser to trace the desired 3D object into a block of gel. Due to the non-linear nature of photoexcitation, the gel is cured to a solid only in the places where the laser was focused, while the remaining gel is then washed away. Feature sizes of under 100 nanometers are easily produced, as well as complex structures with moving and interlocked parts. Yet another approach uses a synthetic resin that is solidified using LEDs. In mask image projection-based stereolithography, a 3D digital model is sliced by a set of horizontal planes. Each slice is converted into a two-dimensional mask image. The technique has been used to create objects composed of multiple materials that cure at different rates. In research systems, the light is projected from below, allowing the resin to be quickly spread into uniform thin layers, reducing production time from hours to minutes. Commercially available devices such as Objeconics apply the resin via small nozzles. Metal wire processors, laser-based wire feed systems, such as laser metal deposition wire, feed wire through a nozzle that is melted by a laser using inert gas shielding in either an open environment, or in a sealed chamber. Electron beam free-form fabrication uses an electron beam heat source inside a vacuum chamber. It is also possible to use conventional gas metal arc welding attached to a 3D stage to 3D print metals such as steel and aluminum. Low-cost open-source RepRap-style 3D printers have been outfitted with Arduino-based sensors and demonstrated reasonable metallurgical properties. From conventional welding wire as feedstock,